Hello everyone, welcome to lecture 12 on numerical analysis. So in the last class we have seen Newton-Raphson method. Okay, Newton-Raphson method and iterative method, bisection method. Those three methods are for solving algebraic equations. Okay, algebraic or transcendental equations. So now we are taking another methods, that is to solve system of linear equations, solution of simultaneous linear algebraic equations. So in that we are going to concentrate on only iterative methods. Okay. So now uh, this is a lecture 12. Yeah. So now let us start with what is meant by linear equation. What is meant by a linear equation? So we already know that an equation is a expression which is equated to some value is called an equation. So now when you speak of a linear, an equation of the form, an equation of the form, so ax plus by plus c is equal to 0. If you are going to take with the two variables, then ax plus by plus c is equal to 0. So is called linear equation. Is called linear equation in two variables. In two variables. Okay. So similarly we can have a linear equation of a three variables also, that is ax plus by plus cz equal to some 0. Okay. So this is a equal to say some d. Instead of 0, if you say some d, then this is going to be an equation, linear equation in three variable. So this is linear equation in three variable. Okay. So already we have studied in previous classes how to solve linear equations which have two variable. So that is by elimination method or cross multiplication. Suppose say there are two linear equations. So a1x plus b1y is equal to c1, a2x plus b2y is equal to c2. So we know how to solve this. So by elimination method, so that is we multiply this into a2 times and this into a1 times, then we remove this x. Okay. Then we get a value for y and we back substitute it and we get the value of x. Okay, that is by elimination method. Or another method we have cross multiplication method or by Cram's rule. So whatever, there are several methods to solve linear equations. Okay, linear equations, elimination method or by cross multiplication. So there are several methods to solve linear equations in two variables that we have studied in previous classes. So now what we are going to do, we take a system of linear equations. Suppose let the system of linear equation be a1x plus b1y plus c1z equal to d1, a2x plus b2y plus c2z equal to d2, and a3x plus b3y plus c3z equal to d3. So we call these linear equations a system. We call this linear equations a system. Why? Means all these three linear equations have a single solution or the same solution. Okay, so that means whatever the x and y z values satisfied by equation 1, so they are also satisfied by 2 and 3 also. So that means all these three equations have a same solution, common solution, therefore we call it as system. Okay, so we know few things how to convert this. This is of the form, if you convert it into matrix, then it is going to be a form ax is equal to b form. A is a coefficient matrix, So okay, so which has a1, a2, a3, b1, b2, b3, c1, c2, c3, and this is x, y, z. So which is equal to the coefficient constant matrix, that is b. Okay, so we are going to convert this into matrix, and we do some operations to this coefficient matrix, either to reduce it to upper triangular or to lower triangular. Then we go on back substitution, we get x, y, z values. Okay, that is what we call direct methods. So now in the iterative methods, okay, so this is transposed. Okay, you take this as b1 c1. So this can be written as, the coefficient matrix can be written as so a1, b1, c1, okay, a2, b2, c2, a3, b3, c3. Yeah, so now if you multiply a1x plus b1y plus c1z is equal to d1, we get this linear system of linear equations. Okay, so we convert this into the matrix form, and we see how to solve this matrix to get x1, x, y, z. So that is direct method. In the iterative method, all these system of linear equations cannot be solved by iterative method. So therefore, so a system of linear equation is solvable by iterative method if only this condition is satisfied. Okay, so that is when you convert this into the matrix, so diagonal elements, that is a1, b2, c3, so on. So all these absolute values of a1 must be greater than b1 plus c1, that is other two. Absolute value of b2 must be greater than a2 and c2. Absolute value of c3, that is, this must be greater than a3 and b3. So then only this is satisfied. Okay, the condition is sufficient but not necessary. That is, if this condition is satisfied, the this system has solution if this condition is satisfied. Okay, so this is sufficient. So necessary means if this is satisfied, then this has a solution. No, so it is only sufficient condition, that is, the system has a solution if this is satisfied. Okay, yeah. So that means instead of saying this condition, we can also say this condition as when you take this coefficient matrix, in the coefficient matrix a1, b2, and c3. Okay, so this coefficient matrix, in the coefficient matrix a2, b2, c2, and a3, b3, c3. So these diagonal elements, what we are talking about, this a1, b2, c3. So these diagonal elements must be greater than the other two, means that must be diagonally dominant. Diagonally dominant. So dominant means they must have very large value. The diagonal elements must have very large value compared to b1 and c1, other two elements. Okay, then we say that the system of linear equation is solvable. Okay, so in this iterative methods of solving simultaneous linear algebraic equations, we have two methods for our syllabus. That is, first one, Jacobi iteration method or Jacobi method. Okay, so the question will be asked like this for 5 marks. Describe Jacobi iteration method to solve system of linear equations. Okay, this question may be asked for some time for 5 marks. Okay, so now it tells you what is the Jacobi iteration method. Okay, it is an iteration method given by the scientist Jacobi. Is a famous scientist Jacobi. You have also heard of Jacobian matrix, the first or second semester. So this is that Jacobi who gave a iteration method to solve a system of linear equations. So now let us see what is that method. So consider the system of equation a1x plus b1y plus c1z equal to d1, a2x plus b2y plus c2z equal to d2, and a3x plus b3y plus c3z equal to d3. Yeah, so we know that this system has solution. So this is the system has solution only if it is diagonally dominant. The coefficient matrix is diagonally dominant. That is, absolute value of a1 is greater than b1 plus c1. Absolute value of b2 is greater than absolute value of a2 and absolute value of c2. Absolute value of c3 is greater than absolute value of a3 and b3. Okay. So then the iterative method can be used for the system 1. So for that we are going to solve for x, y, z. So when I solve for the first equation for x, so first equation I am going to solve for x. Second equation I am going to solve for y. And third equation I am going to solve for z. So when I solve this system of equation for x, y, z, we get this system x is equal to, so what was x? So if you take if you solve this system by, if you solve this system for x, then we get d1 minus b1 y1 minus e1z divided by a1. Okay, so that is, we get x is equal to 1 by a1 into d1 minus b1 y minus c1z. So similarly, so now we are going to solve the second equation for y. So taking all other terms to the right hand side, so this becomes d2 minus c2z minus a2x. So y is equal to 1 by b2 into a2x, 1 by b2 into d2 minus a2x minus c2z. So similarly we get z3. So when you solve the third equation for z, we get z is equal to 1 by c3 into d3 minus a3x minus b3y. So when we have this system, when we have converted that system, that means when you solved for x and y, we get this expression. So this expression, getting this expression is very, very important, because we are setting the system of linear equations to the iterative method. Okay, so now initially we are going to take, so what is the initial value we are going to take? x0, y0 and z0 are the initial values of x, y, z respectively. Then we get the first iteration as, so this bracket we have written is for first iteration, it is zeroth iteration, that is x0, y0 and z0. See here, in place of this, in place of y, z, x, z, okay, in place of x, y, z, we are taking x0, y0 and z0 as initial approximations. So then we have x1 is equal to 1 by a1 into d1 minus b1 y0. In place of y, we have y0. In place of z, we have z0. Okay. Yeah, this is the first iteration. For first iteration, we are going to get this. So this is first iteration. So that is, in place of x, y, z, we are going to take the initial values. Okay, x0, y0 and z0. So this initial value, sometimes it may be given, or sometimes we may start with 0 or we may start with 1. It is left to according to the question. Okay. So after getting the first iteration, this whole if we get all x, y, z, so then this whole thing is for first iteration. Okay. For the second iteration, you are going to use x1, y1, z1 values. Okay, again using these values we get the second iteration. So x2, so x2 is using y1, z1, y2 is using x1, z1, z2 is using x1, y1. This is second iteration. So if you find all this x2, y2, z2, then this is for second iteration. This is for second iteration. So this procedure is to be continued till the convergence is assured. Okay, convergence is assured, correct to required decimals. So correct to required decimals. Please correct it. Okay. Yeah. So now, so let me repeat once again. So we have a Jacobi iteration method to solve a system of linear equations. We came to know what is a system of linear equations, and we are going to solve this. Okay. So let a1x. I am restricted to only 3 variables here. If we can generalize this to n variables. Okay. So how to generalize this to n variables? We can have up to c1, d1, etc. so on, n variables. Okay. Yeah. So now let us restrict for 3 variables. We shall explain this for the 3 variables. Same thing can be continued for the 4 variables or 5 variables, whatever. Yeah. So now we have the system a1x plus b1y plus c1z equal to d1, a2x plus b2y plus c2z equal to d2, and a3x plus b3y plus c3z equal to d3. So let us assume that this system is solvable if absolute value is mod a1, that is absolute value of a1 is greater than absolute value of b1 and c1. So these two, and this is diagonally dominant. In simply speaking, this is the simply the coefficient matrix of this one, okay, of system 1 must be diagonally dominant. So of system 1 must be diagonally dominant. So that means all the diagonal elements are very much larger than the other two entries. Okay. So then the iterative method can be used for the system 1. So this is a system 1 we have. So for that, what we are going to do, in the first equation we can solve for x, in the second equation solve for y, in the third equation solve for z. So then we get the system of equation in terms of x, y, z like this. Okay. Yeah. So now we have to start iteration process with this step. So when you come to this step, you can start iteration process. So that is, given system of linear equation, you have to write in this form. Given system of equation, we have to write in this form. So that is, we have to solve for x, y, z. So when you solve for x, y, z, so call it equation 2. So now go for the initial values x naught, y naught and z naught. So taking x naught, y naught and z naught as initial values, so go for the first iteration. X1 is equal to, so here we are using x, y naught and z naught in x1, and x naught and z naught in y1, and x naught and y naught in z1. Okay. So when you find this x1, y1 and z1, this is the first iteration. So assuming this x1, y1 and z1, okay, we go for the second iteration, that is x2, y2 and z2. So this iteration is to be continued till the convergence is assured. That is, to correct the required decimals, up to 4 decimals or 5 decimals, whatever. So now we shall go for an example, then we shall understand. Okay. So now solve the system by Jacobi iteration method. So now looking at this system easily, you can see that the diagonal elements, okay, diagonal elements are much larger than the other two elements. So you can see that, so mod 10 is greater than, okay, mod 10 is greater than mod 5 plus mod 2, correct? And here also mod 10 is greater than mod 4 plus mod 3. Here also mod 10 is greater than mod 6 plus mod 1. Okay. Here 5 and 2 are values of y and z. Here 4 and 3 are values of x and z. Here it is x and y. Okay. So we can clearly see that this system can be solvable. can clearly see that this system can be solvable. So let us see how to solve this system of linear equation. Okay. Yeah. So that means whenever they ask for the iterative methods, so they give the system of linear equation to be diagonally dominant. Okay. So solution, here we can see that the diagonal elements are dominant. Okay, hence we can uh, further move to the iteration process. Hence the iteration process can be obtained, can be applied. So that is the coefficient matrix. So that is the coefficient matrix. What is the coefficient matrix? We can write. So 10 minus 5 minus 2, 4 minus 10, 3, 1, 6 and 10. So this is the coefficient matrix is diagonally dominant. So this is condition we have to write. Okay, that means we have to check this condition before going for the iteration process. Diagonally dominant. Okay, so how to say that how we say that this is diagonally dominant, since mod 10 okay is greater than mod 5 plus mod minus 2, and mod 10 is greater than mod minus 10 is greater than mod 4 and mod 3. Okay, and mod 10 is greater than mod 1 plus mod 6. Okay, so that is each diagonal entry is greater than the other two. So this condition you have to check before going for iteration process. So this is important. Okay, so this condition you have to check always before going for iteration process. Yeah, so now see what happens. Now by Jacobi iteration method, solve for x, y, z. By Jacobi iteration method, solve for x, y, z. Solving for x, y, z, we get. So now look at the first one. So this is the first one. When I solve for ax, so this is going to be 3 plus 5y plus 5z divided by 10. Okay, solving for x, y, z, we get x is equal to 1 by 10 into 3 plus 5y plus 2z. Similarly, solving the second equation. So in the second equation, so first one I have solved for x. So now solve for y. So when you solve for y, this is going to be 10y if you take this side. So this is going to be minus 3 because plus 3. So 4x plus 3y plus 3 divided by 10. And solve for z using third equation. So now y is equal to, so 1 by 10 into 3 plus 4x plus 3z. See that when you take ax here, in the RHS there is no x. If you take y in the LHS, there is no y in the RHS. Okay, that you have to be very careful. So carefully solve for x, y, z. So z we have minus 3 minus x minus 6y. Okay, so when you set this step, okay, after this step the iteration process starts now. Say this is equation 1, so this is equation 2 and this is equation 3. So now we have to use for first iteration we are going to use for the first iteration let the initial values be so let us start with 0 0 0. Okay, that is x0 y0 and z0. So using this in 1, using these values in 1 2 and 3, so we get x is equal to, so x is equal to 1 by 10 3 plus 5 into, what is the y value? Y value is 0, so 5 into 0 plus 2 into 0, so this is 3 by 10 which is equal to 0.3. So this is what? x1, the first iteration. Similarly, the first y iteration, so that is 1 by 10 into 3 plus 4 into x is 0, 3 into z is 0, so that is also 3 by 10, so we get 0.3. Similarly, the z1, so 1 by 10 into minus 3 minus x, so that is 0, minus 6 into 0, so this gives minus 3 by 10, so which is equal to minus 0.3. Yeah, so now we got what? The first iteration values are 0.3, 0.3, 0 minus 0.3, so these are the first iteration value. First iteration values. Okay, so now for the second iteration, use these values in 1. So use these values in equation 1, 2 and 3 to get second iteration. Okay, so that is x2, the second iteration, so 1 by 10 into 3 plus 5 into 0.3 plus 2 into 0.3, so this gives, so minus 0.3, so this gives 0.39. So y2, so that is 1 by 10 into 3 plus 4 into 0.3 plus 3 into minus 0.3, so this gives 0.33. Okay, so now similarly so let us go for a z2. So z2 is 1 by 10 into minus 3 minus 0.3 minus 6 into 0.3, so we get minus 0.51. So therefore the second iteration values are are 0.39, 0.33 minus 0.51. Okay, so these are the second iteration values. So now look at the first iteration values. First iteration values are 0.3, 0.3 minus 0.3, and second iteration values are 0.39, 0.33, 0.51. So we have got an improved roots now. So now using these, we go for the third iteration values. So using these values in 1, 2 and 3, we get third iteration values. Okay, so that is x3. So x3 is equal to, again same thing, 1 by 10 into so on. So directly I am going to write the values. 0.363, y3 we get as 0.303, and z3 we get minus 0.537. Okay, so use this values. This is the third iteration. So fourth iteration, so using these values in 1. Okay, so fourth iteration we get the x4 as 0.3441, y4 as 0.2841, the fourth iteration as z4 as minus 0.5181. Okay, so next for the fifth iteration, so we have x5 as 0.3384, y5 as 0.2822, z5 as 0.5048. Okay, yeah, now look carefully. We can have an approximation here. So this is 0.34. Okay, so this is also 0.34 approximately, because 8 is here, we can increase this one. So this is 0.4. So this is 0.28 and 0.28. So here also minus 0.51. Here we can increase this as 5, and this can be increased 0.51. So this is minus 0.51. So therefore we can say that the convergence has been occurred. That means up to 3 decimal places we have the convergence. So therefore the approximate values of x, y and z are, so what are the values? 0.33, 0.28 minus 0.51, corrected to 2 decimal places. Okay, corrected to 2 decimal places we have obtained. If you want up to 3 decimal places or 4 decimal places, we need to continue the iteration process. That's it. Okay, so here we have stopped for the 5th iteration. So I hope you have understood this. So this is very easy if you convert the given system into this form. When you convert given system into this form, that is solving for x and y, z, so then afterwards it is very easy. Just go on iterating. So take x naught as 0, 0, 0, then we get the first iteration, use these values in 1, 2, 3, we get the second iteration, and use the second iterated values in the next one, we get third iteration, fourth iteration and fifth iteration and so on. So, therefore, the approximate values of x and z are obtained as 0.33, 0.28 and minus 0.51 corrected to two decimal places. Okay. So, this is how we are going to solve using Jacobi iteration method. This is how we are going to solve system of linear equations using Jacobi iteration method. So, further we shall continue in the next class. Okay. Thank you. So, if anything not understood, please ask me. Okay. Thank you.